Okay, let's continue with our discussion on what was it? Current division. Okay, current division. So, any questions before I go to the example? We looked at voltage division. We looked at an example for voltage division. Then we looked at current division derivation. And then here's the example. So, any questions? Okay. One thing I'd like to mention is there were several students who were who emailed me and also left feedback about homework, which I understand can be very confusing because I use kind of like a, this class is a little bit different when it's structured. So again, on the first day of class and in the syllabus, I point out that homework is considered assigned once the topic is covered in class. I will elaborate on that a little bit. It's like when I first introduce a topic in class, consider it assigned, okay? Because a topic might take 1 or 2 classes to cover, you can always get started on the homework because some of the material will be covered in one class and some of the material will be covered in the next class. So again, as a note to all students, once I introduce a topic in class, it is your responsibility to look at the homework. All the homework assignments are posted online at the beginning of the quarter for this specific purpose, because students, again, it is the students' responsibility, or we would assume that students are responsible enough to actually go through the homework assignments and look at it. The due dates on there are set so that students have Canvas reminders, okay? Right now, all the due dates for homework were set in June. At the beginning of the quarter, all of the homework assignments are kind of bunched together because they cover some of the fundamental topics that you have already learned in physics. Again, some professors cover it, some professors don't, because we expect students, if you have taken a prereq class, we'd expect you to retain some of that information. So at the beginning, I do it a little differently. I do want students to actually, some students might have forgotten, some might have taken the prereq class a long time ago. So I give some homework assignments at the beginning that are bunched very close together. But as I'd like to say, that it's not something that you haven't seen before. I do cover the topics in class and I do assign the homework, but just because of the way the schedule is Monday, Wednesday, Friday, if I cover one topic on Monday, another one on Wednesday, another one on Friday, that's like 3 classes or maybe 3 or 4 different topics within like 5 days. So the homework assignments for all of those would naturally be bunched very together. Okay, so that's the specific reason why it's like that. Once we get done with chapters 1 and 2, that's when they'll be spaced a little bit further apart. But again, homework is considered assigned once a topic is introduced in class, and it might take 1 or 2 classes for a topic to be covered. In this case, we started voltage division last class, and we introduced current division last class. We'll finish current division today. So I would automatically assume, not assume, but I'm letting students know that you should have already begun doing the voltage division homework because it was covered 2 days ago. So this is for everyone. It's not just any specific student. This is for all students to know. Okay, do not wait for a due date to be assigned to that homework. Due dates, again, for all homework assignments are set in June of this year, which is actually 2 quarters away, right? It's the end of the academic calendar. As an example, again, voltage division was introduced 2 days ago, so students are expected to begin working on that homework. Okay, all right, let's continue with this current division example. We saw both in voltage and current division that we would want to find REQ. So the first step for current division, we want to find REQ. If you want to find REQ, remove the source. You have open terminals. And now you want to determine REQ between those open terminals. So this is R1, R2, and R3. All 3 of them are in parallel. REQ is simply the reciprocal of 1 over R1 plus 1 over R2 plus 1 over R3. Someone do this calculation for me, please. Thank you. And again, as a reminder, the instant verification check is that 6.667 is smaller than 10, which is the smallest resistor in that network. If you get a value that is larger than 10, like 11 or 11.6 or something, that means there's an error in your calculation. So you need to train your brain to think of these tiny tips and tricks so that you can know when your answer is correct or incorrect. So this was 6.667 ohms. And then REQ, sorry, not REQ. I1 would be a fraction of the current source, right? So current source is IS, and the fraction is given by REQ divided by R1. In case you have forgotten, that was the derivation, right? REQ divided by R1. So what do we have? 15 into 6.667 divided by 10. What is the answer? 1.5 times 6.667. Anyone? 10. Thank you. And similarly, you can find it for I2 and I3. I2 would be IS times REQ over R2, and I3 would be IS times REQ over R3. That's it. Any questions? Let's take a 10-second pause. Let me know if you have any questions. The procedure, the equation, everything makes sense. Okay. Again, take it step by step. Identify the circuit, identify the components, whether in series or parallel, find REQ, and then apply the equation. You can have this equation on your equation sheet. So you can have all the tools in your toolbox, but you should know how to use them and when to use them. Okay. Yes. Sure. Yeah. There could be certain circuits like that. So the question being asked is when would we use this? And the answer is it just depends on each individual person. As always, there might be multiple ways to solve a circuit. So you could have 2 parallel lines, 3 parallel lines, or 4 parallel lines. You would determine the voltage across that network, and you could just find current that way. Some students like to do that. But if a question specifically asks, solve this using current division, then I want to see the implementation of this equation. Okay, there shouldn't be any derivation of Ohm's law and then applying voltage and stuff. Obviously, this equation, current division and voltage division equations, are derived from Ohm's law, right? We apply Ohm's law, we find the voltage across that nodes, and then we apply Ohm's law once again to find the current. This is kind of like a shortcut where you eliminate 2 steps or 1 step. All right, makes sense to everybody? Okay, so current division and voltage division homework, consider them assigned. Okay, they have, I think, 3 to 4 problems each. I don't think there are any tips or tricks to it. So if you have any issues, reach out to me. Solving this by logic. So one final point before we move on. 10, 30, 60. The lowest resistor would have the highest current, right? Opposition is low, so the flow would be high. You can see current for whatever current we get for I3, I1 would be 6 times I3. I2 would be half of twice as much as I3. Does that make sense? So you could solve it just using logic and intuition if you want to verify your answer that way. Does everybody see that? All right. Node voltage analysis and mesh current analysis. These are the two final topics of analysis techniques in this class. And then at the end, we'll put it all together and apply it to a network theorem. Okay. So before we get into that, I want to introduce what is a node voltage and what is a mesh current. Okay. This is a very important topic, guaranteed 20, 30 point problem in the final exam. This is one of the most important, not one of the, two of the most important analysis techniques. Okay. So far, we learned about reducing a network of resistors down to one single resistor and then applying Ohm's law and solving it that way, right? Solving a circuit that way. But oftentimes, there are circuits that cannot be reduced. Okay, you cannot reduce a circuit down to one single resistance. One of the most common examples would be if you have multiple sources in a circuit at two different places and you cannot combine those sources. So if you have, let's say, a voltage source, two voltage sources, two current sources, or one voltage source and one current source, you cannot combine them if they are in different parts of the circuit. So you cannot reduce those resistors down to one single resistance. And if that's the case, then you would use these kind of techniques, which is node voltage analysis and mesh current analysis. Okay. All right, so let's start with node. What is a node? Any junction in an electrical circuit is a node. Okay. So a node is basically a junction in an electrical circuit where two or more components come together. Okay, where two or more components come together. If you have one resistor connected to one source, that is a junction point, and that is a node. It might not be very evident from a circuit schematic, but these corners are nodes. This is also a node. This is also a node. Okay, anytime two connections come together or two wires come together, it is a node. A mesh is a simple loop. Mesh is a simple loop. When we talked about KVL, I pointed out that if you start at a point in a circuit and you go around the circuit as if you were driving a vehicle and you come back to the exact same point, that is an electrical loop. And you can take multiple loops, right? You can have a loop inside of a loop. So a mesh is a simple loop that does not contain any loops inside it. And I will explain what I mean by that. So in this example schematic right here, if we start at the bottom left corner, how many ways do we see, or how many possibilities are there for it to come back to the same place? There are two of them, right? We can start here and we can return back to that same point via this loop or this path. So once you have a closed pathway, that is a loop. So it's a loop one. And we can also say, if we start from the exact same point, we can come back to that exact same position. I can call that loop two. There's also a third loop on the right. Of course, if we start at point A, we can call that loop three. But let's not focus on that for now. Look at loops one and two. What can we say about loop one and loop two? I can say loop two is bigger and it encompasses loop 1 inside it. So loop 1 is sitting inside loop 2, so to speak. Does that make sense to everyone? Right? Loop 1 is inside of loop 2. That's just a way of, it's just words. However, well, not however. So L1 and L3 both sit inside L2. Okay, loop 1 and loop 3 are both inside loop 2. All three of them are electrical loops. However, loops 1 and 3 are the only ones that are meshes. They are simple loops. They do not contain a loop inside it. Loop 3 is not a mesh because it has other loops inside it. I'll take a 10-second pause and let you think over that. So again, going back to the definition I wrote out, a mesh is a simple loop, and a simple loop is one that does not have any other loop inside it. Any questions? Any questions at all? Yes. L1 and L3. L1 and L3. So this and this. Let's call it L1. And then I'll call this L2, the outer loop. The outer loop is not a mesh. L1 and L3 are meshes. Identifying meshes are easy. You look at a circuit, you see a closed pathway, and that's a mesh. That's it. Identifying loops is a little more complicated, especially if you have multiple components and larger circuits, but identifying meshes is very easy. Okay, so you look at a circuit, closed loop, doesn't have any other loop inside it, that's a mesh.
Professor,
Yes.
what does the symbol at point A mean?
Where?
The like three.
Oh, this one.
Yeah, that.
Yeah, ignore that for now. That stands for ground or earth. It doesn't affect the circuit in this case.
Okay, thank you.
Yeah. So as I was saying, identifying meshes are easy. The first thing we want to do when we deal with these kind of analysis techniques is to identify the nodes in the circuit and all the meshes in the circuit. Okay. So in this case, we identified the meshes. Loop 1 and loop 3 are both meshes. In this case, they use A and B. So either ways, it doesn't really matter what notations you give it. Okay. We have two loops in the circuit. Sorry, we have 3 loops in the circuit, but only 2 meshes. Right. Now, junction points. They're already identified for us. We have A at the bottom, B, C, and D. Why is this not a node? So we can see there are 6 junction points on there. But why do we only have 4 nodes? Why not 6? Anyone? Yes. Yep. That is the exact correct definition. That's the answer. Just because this is bent doesn't mean it's different. Remember, a wire is the same as a connecting point, as a dot, right? A wire can be short, wire can be very long. Circuit schematic doesn't change that fact. So I could draw this circuit like this. This would be A. Just because the wire is bent in that schematic doesn't mean it's a separate node. It's the exact same node. Node is a junction of two or more components coming together. So this entire line right here, it's not just a dot, right? This entire connection is a node. This entire connection is a node. This entire connection is a node, including that wire. So do not be confused with just one tiny dot, okay? The entire length of that wire is the exact same node. A real life example is if you plug in your extension cable, whether it's 25 feet or 50 feet or 100 feet, into a power outlet, you are now pulling that power outlet 100 feet away. But that doesn't change the fact that it's still powered and you shouldn't stick your finger in it, right? So that's the same concept. It's the exact same wire, it's the exact same, sorry, it's the exact same node, no matter the length of the wire. All right, so once we have identified the nodes, we label them A, B, C, D in this case. And because we're talking about node voltages, we need to have a reference point for measurement. Okay, we need to have a reference point for measurement. In this case, that reference point is noted as A. And it is marked with this symbol. This symbol refers to ground. So, three horizontal lines in the shape of a triangle. It's referred to electrical ground because it literally goes into the ground. You might have come across, especially outside a building or outside a transformer or a light pole, you might see a wire going directly into the earth or into the ground. It's to pass off any of the excess current that might be coming through. So again, we won't bother with it too much. This is known as ground or earth. So even if this was not there, it does not change the circuit or doesn't affect our analysis. Okay. Because we are dealing with voltage in a node voltage analysis method, voltage is always measured between 2 points. There's a reference point, and then there's the point of measurement, right? Reference point is minus, measurement point is plus. We always want to identify a reference point. In this case, the reference point is identified as A. So VA is the reference, and every other node is measured with reference node A. Okay. Now the ground or earth would be in some other part of the circuit. In this case, it's just shown that node A is ground. It does not affect it right now. So ignore that part. And when I say VB, what I actually mean in this case would be VBA. Because my A is the reference, I'm going to say A is my second point of notation. So VB for this circuit, node B, is measured with reference to A. Okay, A is the point of reference, B is measured. So I'm trying to find out the difference in potential between points B and A. That difference could be plus or positive, or it could be negative. Doesn't really matter. But at the beginning of my problem, I want to note reference node is A. So VA is reference. So anytime I measure voltages at any other node, and I just say VB, VC, or VD, what I'm actually referring to is VB measured at A. Does that make sense? Your reference point is at A. Similarly, you have VC and VD. VC and VD. Is VCA and VD is VDA. Okay. VB, VC, and VD. And then we have the component voltages V1, V2, V3, and V4. We'll look at that next class. I went over like a minute over time. Didn't even realize that. All right, let's stop class here today, and I will see you all on Wednesday.